Okay, as promised, we're going to wrap up this log and exponential function unit with some application problems. I'm just going to go through and do an assortment of application problems from 5.6. There's a lot more than what I'm going to be doing, but I just wanted to give you a good representation so that you can have some reference to move forward on. All right, so I'm going to have to keep flipping back and forth here because I'm going to be pulling up the book. Because the first problem I'm going to do is number 2 in the exercises. It says the information in example 1 allows us to use the function a of t equals a sub 0 times e raised to the negative 0.0001216t to approximate the amount of carbon-14 remaining in a sample where t is in years. Use this function in exercises 1 through 4. So number 2, we're going to look at carbon-14 dating. A sample from a refuse deposit near the Strait of Magellan had 60% of the carbon-14 of a contemporary living sample. Estimate the age of the sample. All right, so we're able to use what percentage of carbon-14 remains after something has died and been decomposing. And that'll help us to estimate how old the sample is. Okay, so let me switch back to my PowerPoint here so I can do a little writing. So the original function looks like this. A of t equals a sub 0 times e to the negative 0.0001216 t. Okay, and t is the time in years. Okay, so in our question, it said that the sample, the refuse deposit, has 60% of the carbon-14 remaining of a contemporary living sample. So a sub 0 would be the initial amount. You know, sub 0 means you haven't, nothing has started decomposing yet. You're at ground zero. You're at the very beginning. So that would be like the contemporary living sample would be how much carbon-14 it has. This is just a typical decay type exponential function. The t is time in years, and if you multiply all that out, it'll give you how much of the carbon-14 in this case remains in the sample. We don't know how much, but we know what percentage of the original remains. So what we're going to do is we're going to leave a sub 0 in there as a variable. T is what we're solving for, so that stays in. But a of t, that's how much would be remaining now in that sample. It's 60% of a sub 0, 60% of the original. So 60% times a sub 0. Well, now we've got a sub 0 on each side that can be divided. Sorry. Because we know that the initial amount's not 0. So we can divide both sides by a sub 0, and that's going to leave us with 0.6 equals e raised to the negative 0.0001216t. And now we're down to one variable t to solve for. Wants to figure out that time in years. So we have an exponential equation, and the variable is in the exponent here. And we can't get the bases the same, but one of the bases is e. So let's go ahead and take the natural log of both sides. Well, the natural log of e to a power is just going to leave you with that power. All right, then to finish solving for t, we're going to take the natural log of 0.6 and divide by negative 0.0001216 and see what that comes out to. I'll let you do that in your calculator there at home. And I'm going to go and do it in my calculator here in my hands. All right, and I get 4,200 0.868616. And the question asks us, just estimate the age of the sample. So you could say that the age of the sample is approximately 4,200 years old. Based on the amount of carbon 14, the percentage of carbon 14 remaining. Well, there you go. All right, next question. Has to do with radioactivity, cesium-137. That was number 6. Radioactive cesium-137 was emitted in large amounts in the Chernobyl nuclear power station accident in Russia on April 26, 1986. I remember when that happened. Recently, I've been seeing articles about lingering effects of the radioactivity. The amount of cesium-137 remaining after X years, an initial sample of 100 milligrams, can be described by that exponential function. A of x equals 100 times e to the negative 0.02295x. You're going to estimate how much is remaining after 50 years. So you can put 50 in for x, see what you get. And then ask yourself, is the half-life of cesium-137 greater or less than 50 years? Okay, so half-life, like if you're starting with 100 milligrams, how long does it take for the radioactive decay to work so that you end up with only 50 milligrams, end up with half of it? What's that half-life? You're going to estimate the half-life of cesium-137. Okay, so that function was a of x equals 100 times e to the negative 0.02295x. Okay, so when x is 50 years, put in 50. All right, I'm going to do that on my calculator here at home. So I don't have to keep switching back and forth between the calculators. All right, so e raised to the negative 0.02295 times 50, and then that times 100. And I'm getting around 31.7, and that would be milligrams. So the half-life is actually less than 50 years. Because we started out with 100 milligrams, and we are left with less than half after 50 years. So the half-life occurred before the 50-year mark. So we got to figure out, well, when is that half-life? When does it happen? Okay, so if we started with 100 milligrams, when does it reach 50 milligrams? When does it get to half of that? So we got 50 equals 100 times e, negative 0.02295x. Divide both sides by 100, you'll have 1/2 equals e to negative 0.02295x. Then take the natural log of both sides. So we have the natural log of 1/2 equals negative 0.02295x. Okay, so I'm going to go and put this in my calculator. I'm going to take natural log of 1/2, and I'm going to divide by negative 0.02295. And I get 30.2 years. So 30.2 years is the half-life when it reaches half of the original amount. All right, next. Okay, next one, we're going to switch gears. We're going to get away from the archaeology and radioactivity and all that. And we're going to go into a financial situation. Let me pull that one up. It's on the next page, page 395. And it's on the bottom, number 18. Question says, an amount A in a bank account after X years is given by A of X equals 450 times 1.06 to the X power. Okay. So then we're trying to figure out first how much is in the account after 2 years, how much is in the account after 20 years, then after how many years will there be about $2,300 in the account. Okay, so the amount A in a bank account after X years is given by A of X equals 450 times 1.06 to the X power. Okay, so when X is 2 years, 450 times 1.06 squared. So square 1.06 first because it's an order of operations. And then times that by 450. You get $505.62. I don't even have to actually approximate because it actually comes out exactly that. Dang it. Trying to write and I messed up. Try it again. All right, so $505.62. Then it says how much is in the account after 20 years. All right, so you got to put 1.06 to the 20th power first. And then times that by 450. I'm going around to near cent because it is money. So you're going to get $1,443.21. And when will it have $2,300? Okay, so A of X is 2,300. You're trying to see that's going to be the future value. And now you're solving for X because you're trying to figure out the time. So divide both sides by 450. Then you can take the log of both sides. Right side you'll have x times log of 1.06. So x equals that log of 2300 over 450 divided by log of 1.06. Put that in your calculator, see what you get. And you get like 27.99806, something like that. So you could say about 28 years. And there you go. Okay, we'll do 2 more questions with you. Next one's on page 397, number 46. The growth of bacteria in food products makes it necessary to date some products, such as milk, so they will be sold and consumed before the bacterial count becomes too high. Suppose that, under certain storage conditions, the number of bacteria present in a product is f of t equals 500 times e to the 0.1 t, where t is time in days after packing of the product and the value of f of t is in millions. If the product cannot be safely eaten after the bacterial count reaches 3 billion, so I'm looking at 1,000, million, billion, how long will this take? If t is 0 equals 0 corresponds to January 1st, what date should be placed on the product? All right, so let's tackle part A first, of course. So we have f of t equals 500 times e to the 0.1 t. Okay, so that product cannot be safely eaten after the bacterial count reaches 3 billion. So 3,000 million. Because the value f of t is in millions. So we have 3,000 equals 500 times e to the 0.1 t. So divide both sides by 500. You're going to get 6 equals e to 0.1 t. Take the natural log of both sides. You have natural log of 6 equals 0.1 t. So t is going to equal natural log of 6 divided by 0.1, whatever that comes out to. $17.917, etc. So about 18 days. Might as well just say 18 days. So it's 18 days after packaging of the product. So if t equals 0 corresponds to January 1st. In other words, if it's packaged on January 1st, then the expiration date should be 18 days after that, so January 19th. 1 plus 18. All right, and one more. Next page. Oh, sorry, not next page, previous page, the same page, previous column. We're going to look at number 36. Find the present value of an account that will be worth $25,000 in 2.75 years if interest is compounded quarterly at 6%. Page before that has the formula for present value of an account. A is the future value, how much you want in the account in the future. R is the interest rate, T is the time. R and T need to be in the same time frame. So if R is annual interest rate, T has to be in years. And then N is how often you're compounding, or how often you're adding the interest through the year. So you're adding interest on interest, it's compounding. But N is the number of compounding periods per year. All right, so what we're going to do is tackle this question, number 36. You got $25,000 will be the future value. T is 2.75 years. It's compounded quarterly, so N is 4, because 4 times per year. And R is 6% or 0.06. Okay, so let me write down the formula again for you. P equals, and they use a negative exponent. I'm going to go ahead and rewrite it like this. A over, this is how I'm used to seeing it, 1 plus R over N to the NT. You're basically taking the compound interest formula and dividing both sides by 1 plus R over N to the NT. Okay, so future value in our case is $25,000. That's how much it's going to be worth down the road. The time is 2.75 years. Compounded quarterly, so N is 4. And this is going to happen for, it's going to happen at 6%. You have to use your percent as a decimal in the formula. Okay, so to get how much you have to invest now to make sure you have $25,000 in the future, start plugging these values into your formula. Then follow your order of operations to simplify. So you have 0.06 divided by 4. My calculator is old and the buttons keep getting stuck on it. And that gives you 0.015. Oops. It's getting late and I'm tired. Sorry about that. So fix that. 0.015. There we go. And then your exponent is 4 times 2.75. And that gives you 11. That's what I thought, but I was needed to double check it the calculator because I'm tired, my head's hurting. All right. So then we got So we got 1.015 to the 11th power on the bottom. So we're going to take 25,000 divided by 1.015 raised to the 11th power. Okay, then we get 21,223.33083. This is a money problem, so you go ahead and round to the nearest cent. That's, you don't have to go any further than that. Just make sure you round at the very end. Don't round during a problem because then you'll throw off your accuracy. $21,223.33. So that's how much has to be invested now in order to make $25,000 in the future in 2.75 years at 6% compounded quarterly. So there you go. All right, well, I think that's a good mix of application problems. Have fun. They're all exponents and logarithms. I think you guys are ready to do this. All right.